Hello everyone, Mr. Caleb is back with another problem. So, my gosh. Sorry, I forgot to write down which problem this was. Oopsie. It is problem 35. Oh, 33. 33, excuse me. We're doing problem 33. So, what's the problem today, Gus? Calculate the energy required to convert 1.7 grams of ice, originally at negative 12 degrees Celsius, into steam at 105 degrees Celsius. Show all constants and info, drill the meter. Now, when I first saw this, Gus, I was like, wow, this is an easy problem. It's only 5 points. Just plug in the numbers from just plug in Q equals N times C times delta T, which would be easy, I thought. Well, clearly not. So I did some research, and it clearly isn't. So, Gus, you might be inclined to think that we just plug in 1.7 times 4.184, which is the acidified water times 117, right? Because that would make sense, right? Well, Gus, here's the thing. I'm sure you're aware of this, Gus, but let me draw a heating curve for you. Basically, when water it gets to a certain point, like 0 degrees Celsius, which is when water starts to freeze, it will undergo transformation. Correct, Gus? But here's the thing: when water, let's say water freezes, or actually let's say when ice forms up, because that's more equivalent to our example. When ice starts to melt and turn into water, it requires a lot more energy. It requires energy to convert that without the temperature increasing. So in other words, let me show you. So heat or energy. So our bottom axis will be energy into the substance, or let's say energy into, and our upper axis or our y-axis will be temperature in Celsius, right? And this dotted line will be 0 degrees, this dotted line will be 100 degrees. Yeah? So we start at negative 12. So let's just say this is negative 12. And we're going to end at like 105. Right, Gus? So you might think that it would just be a straight line, right? As more energy is put into the substance, the temperature increases linearly, correct? Nope, Gus. Unfortunately, it is not that easy. In order to convert a substance to another substance, it requires energy. So in other words, when the ice hits 0 degrees, it's going to flatline for a second, where the temperature does not change at all, even as energy is being, more heat is being put into the ice. So it's going to flatline for a moment until it has a certain amount of heat, and then it's going to increase again. And then and this is when it turns into water. So now, as you add in more heat to water, the temperature keeps increasing until it hits 100 degrees Celsius, where it starts to turn into steam. And once again, it requires a bunch of energy to convert that into steam before it can heat up again, or before the temperature can increase. Does that make sense, Gus? So it goes like that, and right here it turns into steam, and the same thing happens. It starts to increase until the temperature hits 105 degrees Celsius. So kind of ranted there for a bit, but I'll explain it one more time. Basically, ice is at negative 12 degrees Celsius, Gus, and we add heat into it, and as we add heat into it, the temperature increases. However, once the ice's temperature hits 0 degrees Celsius, it needs a bunch more energy before it can convert to water, and the temperature can keep increasing. So it has to undergo a phase change, and an undergo the phase change needs a bunch of energy. So after it undergoes a phase change, it turns to water, and the temperature increases as we add heat. However, it eventually reaches 100 degrees Celsius. Same thing repeats with ice, but once it gets past steam, the temperature can increase again, and we're trying to figure out how much how much energy is needed to convert negative 12 degrees Celsius to 105 degrees steam. 1 point. So I wrote down a bunch of info before I do this problem. So our specific heat of water, and I'm gonna write C. Oopsie. Sorry. I'm gonna write C water. C in this case just stands for specific heat. I'm gonna do this for Metsudan just because I don't like to write it over and over. So specific heat of water equals, as we know, 4.184 joules per gram. Yeah. Specific heat of ice. Yep, because heat changes as phase changes. Woohoo. Is equal to specific heat of ice is equal to 2.093 joules per gram Celsius. Specific heat of steam is, give me a second. Specific heat of steam is 2.09 joules per gram Celsius. And just two more bits of information we need to know. We need to know how much energy is required to convert from ice to water. So right here, we need to know how much energy is being applied right here. We also need to know how much energy is required to convert water to steam. So right here. And this is represented by delta HF. And delta HF is heat of fusion of water, meaning the amount of energy required to convert ice to water. Or I guess in reverse. If you were to convert water to ice, that's what's called fusion. But since we're adding energy, this is going to be heat. So the heat of fusion of water is equal to 334 joules per gram. So it takes 334 joules of energy to convert 1 gram of ice to water, basically. Sorry if I'm jumping around a bit. This is all new to me as well, yes, to be honest. Anyway, so now our last information we need to know is the heat of vaporization. So how much energy requires to convert 1 gram of water to steam, which is represented by delta HV, so heat of vaporization, which is equal to 260 joules per gram. And I want to note, if you're going to do this yourself, your numbers may be different from mine. For example, mine is specific heat to steam is not all that accurate. Same with water to an extent, probably. And your answer may be a little different if you do this yourself. But these are the numbers I'm using, and they're going to be kind of close to whatever numbers you would use. Probably. We may use the same numbers. Anyway, let's do our work. So for our first step, we're going to convert 12 degrees of ice to 0 degrees ice, which is pretty simple. We already know that. Define Q in this case, it will be Q equals M times specific heat times delta T. So let's go plug that in. So our mass of ice is 1.70 times specific heat. Specific heat of ice is 2.093 joules per gram of Celsius. Then times change in temperature. What is the change in temperature? We're going negative 12 to 0. So 0, which is the final T. So final, I'll write it up here. So change in T is equal to T final minus T initial. Our T final will be 0 degrees and our T initial will be negative 12. So 0 minus negative 12, which is plus 12. So 1.7 times 2.093 joules over grams Celsius times 12 degrees Celsius. My marker's good now. See, you can see that real quick? Probably. I hope I'm saying out loud enough so you can understand me. Anyway, I'm just going to plug this into our calculator. And oops, I forgot to write my unit right here. Anyway, so the grams will cancel out, Celsius cancels out. We're left with 1.7 times 2.093 joules times 12. And this gives us 42.7 joules. We're not done yet though. Just 12 degrees of ice to 0 degrees ice. We now have to convert negative 12 degrees ice to water. Or, yeah. I think we have to convert 0 degrees ice to 0 degrees water. So let's see what that does. A woman just walked by and looked at me like the same. Sorry about that. Look weird. I need to figure out a better place to do this. I don't want to do this in my room. I think this is a pretty good teaching environment like us. Anyway, I leave my calculator right here. That's what it's for. Well, I'm getting a lot of these. Sorry, I'm hurrying up a little because I'm taking one I realize. Anyway, to find out how much energy is required, we just use the formula Q. Q equals M times delta HF. So pretty simple. So just 1.70 grams times 334 joules per G. So mass that. And this cancels out, even though some joules. And our answer is, sorry guys, easier to put, 568 joules. So, if you want to know where we are on the heat curve, we are about right here exact. But now, actually, I probably should explain that. So when we did this, we went from here to here. When we did this, we went from here to here. So now we're right here, right? And now we're going to go from 0 degrees water to 100 degrees water. Which is, once again, represented by the formula Q equals M times C times delta T. So, real quick, this one should be really easy. Because we're going back into familiar territory of 4.184 for water. So 1.70 grams times 4.184 joules per grams Celsius times 100. How do we know it's 100 degrees Celsius? 100 degrees Celsius. How do we know it's 100? Our finals will be 100. Final degrees can be 100 degrees Celsius minus 0 degrees Celsius. So 100 minus 0 is 100. It's crazy. Anyway, the grams cancel out. Celsius cancels out. And we're left with, where'd my calculator go? Oh, alright. Sorry guys. 1.7 times 4.184 joules times 100. We were left with 711 joules. So we have gone from here on the heat curve all the way here. However, we now need to convert from water to steam. So, or actually, more accurately, we need to convert from 100 degrees water to 100 degrees steam. And I'll explain in a second why our formula is this. See, you've already noticed this is almost exactly the same as the other Q formula. So why don't we put, why is delta T not there? You might wonder. Or, I don't know. I'm overthinking it. Basically, I'm overthinking it. I just want to explain something you already know. Anyway, because this is different. Anyway, so I'm getting a bit tired. So our mass is still 1.70. grams. And we're going to multiply by the heat of vaporization, which is 2260 joules per gram. So 2260 joules per gram. Yep. And once again, guess what? The grams cancel out. What do you guess? 1.7 times 2260, which is 3,840 joules. Yep. So now we have gone from here, meter, to here. Oopsie. And now we need to go 100, so we converted to steam. Now we need to convert steam from 100 degrees steam to 105 degrees steam. So from here to here, pretty simple. We're doing Q equals M times C times delta T. Oh no. Uh-oh. My marker is really almost dead. I still should have black one, but it's pretty bad as well. No, it can make it. So we just have just enough marker to make it to the end. So let's speed this up real quick. So 1.70 grams times specific heat of steam, which is right here, 2.09 joules per grams Celsius times 5. How do we know it's 5 degrees Celsius? 100, or so our final temperature is 105, and our initial is 100, so 105 minus 100 is 5. Yep, really that simple. Guess what? The grams cancel out just like last time. So this cancel out just like last time. We're left with 1.07. 1.7 times 2.09 times 5. We're left with 17.8 joules. Wow, I got myself there. 17.8 joules. Oh, we've done it. So guys, we're basically done. All we have to do now is add up all our joules. So 17.8. So we finally reached the end point. We've gone from here to here. So 42.7 joules times and plus. Someone walk by again, guys. Sorry, 42.7 plus 568 plus 711 plus 3840 plus 17.8. My voice hurts, to be honest. And this gives us our final answer. We are left with 5,179.5 joules. Let me see if you can read that. Sorry, my marker is really close to dead. I'll try to rewrite it. Oh. It's really close to dead. So the amount of heat required to get from ice at negative 12 degrees Celsius to steam at 105 degrees Celsius is 5. Oh gosh. It actually is that. 5,179.5. Yep. Don't forget to like and subscribe for more exam bonuses in the future. I might have to do another. I hope you can read this. I really don't. It's like I have to redo these because my marker died. Anyway, have a great day. Thank you for watching.